In this video now we'll start chapter 2, and specifically chapter 2 is on limits, and limits is what creates calculus for us. So first we'll start with a preview of calculus, trying to understand what is calculus about. And you will see that calculus has actually two parts. One is the differential calculus that we focus more on in the beginning, and then we go to integral calculus, and that happens in one variable first and then multivariable. So the differential calculus is about a rate of change. So how things change, at what rate do they change? So that is called the slope, right? The slope, if it is positive, something is increasing. If it is negative, it's decreasing. So you will see that understanding a rate and what it depends on, we understand a lot about systems. Whether it's physics, whether it's a financial system, economic system, any kind of system, engineering systems, anything when there's a change with respect to time, with respect to position, space, anytime there is a change, we understand that change and then we are able to model using differential calculus. In fact, the most famous physics statements, the physics laws, for example, the rate of change of momentum, the Newton's law, second law, is equal to force. So force is the change in momentum. So change, the rate of change of momentum. If you want it higher, basically we define it as, the acceleration, ma. So F equals ma, but a, acceleration, is the rate of change of velocity. And m times that becomes the momentum. So that's just the physics is built on that. And same thing if you look at electromagnetics, you look at engineering problems, finance, investment, the prices of anything, absolutely every field. Okay, even you can bring it to social science, even psychology. Like how does our mind change its thinking, right? The change is about differential calculus. So to start understanding it, if you have a straight line, for example here, negative 2x minus 3, so this line, the slope is negative 2. So as x changes, the function fx, the value of y, is decreasing. So slope is negative. Here, slope is positive. Its value is half. And then here, things are not changing. Okay, so for a straight line, that's where it is. How about if we have a curve? Now we have to see, if you are close to the curve, how does the curve change? Okay, so you can see here, for example, here at this point, if you put a stick there to see, you'll see that this is flat. So locally things are not changing at this point, x equal to 0. But if you look at here, see the change is happening, so we can draw this line tangent to it. And the slope of that is telling us how the change is taking place. So differential calculus is about computing this tangent line, the slope of that, and that's called the derivative. Okay, so it's very, very important to understand changing systems. And as I said, that gives us power to analyze any kind of system. And that's where calculus comes in. So in order to calculate, for example, the slope at this point. So if you know the value of the function at a and fa, and if you take another point, x, so we have a value of the function x and fx. So we can draw a line through these 2 points, straight line. Okay, it's called the secant line. And we can find the slope of this line, right? Very easy. Change in the height, which is fx minus fa, so delta y, over delta x, x minus a. If you look at this triangle, this height is the whole height, which is fx, minus this height, which is fa. So fx minus fa is delta y, and this length is a, and this length is x. So this delta x is x minus a. So delta y over delta x is fx minus fa over x minus a. Now that is not the tangent at this point, right? But if you take the next point here and then draw a secant, that's a better approximation to the tangent here. If you bring it closer, now you have even a better approximation. So as you bring the point closer and closer, as we get closer and closer to infinity, like we keep doing it closer and closer, all the way, where is the line going to? That line in the limit will be the tangent at that point, and that is the slope we are after. And that is what we will define as the derivative of this function at that point. So it comes by approximation by secant lines. So the tangent at this point is basically the slope of that tangent is the limit of the slopes that you get by taking different points. So if you take this one, this is the slope. If you take this point, you'll have a different slope. Take it this point, so you are getting different numbers. What are these numbers going towards? Which number? That number will be the limit, and the slope of that will be the slope of that tangent line. Okay, so that's what we are after. So the secant to the function fx through the point a fa is basically this slope. And then as you take this point x closer and closer, you're getting better approximation. And tangent is the limit that you achieve, and differential calculus is about this derivative, the slope of the tangent of the function at different points, and how the derivative changes as a function x. Okay, that's the tangent line. Some examples. So estimate the slope of the tangent line to fx at 1 by finding slopes of secant lines through 1, 1. So our function is x squared, and at 1, the value of the function is 1, so we have this point. Okay, then you take another point, 2, 4, 2 and 4, and say, okay, let's find a secant, right? So going to GeoGebra, let's delete this. Okay, I think I can go here, delete, okay. And then here, let's plot x squared. That's our function. And we see, let's see where point is this one. 1, 1. That's the point. And next point we're taking is 2, 2, right? 2, 4, and 1, 1. And then we want to draw a secant between these 2 points, a straight line between these 2 points. Okay. So from A to B. Okay, that's the line we are drawing. And let's see, when x is equal to 1, yes, y is equal to 1, so this is it has gotten A and B as the points on the line. When x is equal to 2, y is equal to 4. So this is the equation of the line, which you can, of course, derive yourself. So this is the question here. Of course, I would ask you to do it by hand, but I'm just showing you on GeoGebra. How do we get that? So secant is, what is the slope then? 4 minus 1 over 2 minus 1. So the slope is 3, positive 3. And of course we could get the equation of the line. So if you know a slope m of a line, in this case is 4 minus 1 over 2 minus 1, it is 3. And the function goes through 1, 1. So remember, the equation will be y minus 1, slope 3, x minus 1. And we can expand it, and that'll be the equation of the line. And similarly, if you have another one here, the slope would be 9 over 4 minus 1, 3 over 2 minus 1. And you can also, looks like it's 2.5, and you can also draw it on GeoGebra. Okay, looks like my video vanished. Okay. Now, if we would get the points closer and closer, then of course, as we discussed before, we are getting closer and closer to the tangent. Okay, now a kind of similar idea is when you are, let's say, driving a car on a straight line. So they talk about velocity here. I'll use the word speed, okay, instead of velocity. And in 2 dimensions or higher dimensions, there's a difference. Speed is just the scalar quantity, a number, but velocity has a magnitude and a direction. So here, let's say S is the position of an object. So let's say it's going on a straight line. Okay, so here is a straight line, and we are, here at one point, so this is S here, and it's a function of time. So at different times our position is different. So S is a function of time where we are on this line. So now at time t, we start at time A in the beginning. Okay, and then after some time t, so this is A, and our time is A in the beginning, initial time, and our position will be S of A. Now at a later time t, let's say we are at some other position, S of t. Then what is the average speed? The average speed is st minus sa, or how much distance you traveled during this time and in how much time. Now you could have gotten faster in the middle, slowed down, whatever. So those are instantaneous speeds. But the average speed is, okay, how much distance you covered in that much time. In fact, if you drove forward and came back to the same place, the average speed would be 0 because you haven't moved anywhere. But the instantaneous speed would be that if you look at a time t and look at right after that time, t plus delta t, like right after that, where was the position? And you say, okay, where am I at time t plus delta t minus where I am at time t, and how much was the change in my position in a very small amount of time. And how much delta t? Take delta t to be very small, maybe 1 second, 0.5 second, 0.0. So as you reduce the time delta t, you will see you're getting a better and better estimate of the instantaneous speed, just like the slope of that function. If we take the point x and the next point, right, we had the point A, then we took x. If we take x closer and closer to A, we are approximating the slope better and better. Okay, same thing here. Okay. So, not working. Anyway, it doesn't matter. So that is the difference between the average speed and the instantaneous speed. Instantaneous speed is the derivative of the position, the slope of the position function at that point. Okay, but average is, over the time. Okay. A rock is dropped from a height of 64 feet. T seconds later, okay, is given by this function. So as you can see, as time increases, the st value will decrease. Find the average speed of the rock or each of the given time intervals from here to here. So the average speed for this one is s at time 0.5 minus s at time 0.49 over 0.5 minus 0.49. And plug this function with 0.5 for t, and here plug the function for t equals 0.49. Okay, you can easily compute this here, so it's this. And if you plug in this, you'll find out is this one. Okay, so this is taking the average between 0.49 and 0.5 versus 0.5 to 0.51. So if the speed was changing a little bit between that time, and it is, you can see that. So the average is, somewhere between these two. Okay. Now this is differential calculus, where the focus is on finding the change of the function, the value of the function, as you change the domain, like for example, x value or time, t value. The opposite problem of that is integral calculus. And integral calculus means instead of finding the slope, how the function is changing instantly at that point. So here, how is the function changing instantly? That's the slope. It's negative. Function is decreasing. So it's a very local information. What is happening to the function now? As compared to this, if you look at a to b and say, what is the area of the function? Like the performance of the function. So it's used in a lot of things. For example, how much work is done, all kinds of stuff, integral calculus. We find the areas, volumes. For example, how do we find the volume of a sphere? You're given a formula, but how do you derive it? You need integral calculus. So now if you're given a function and you want to find the area, just like to find the slope, we took approximations. We took 2 points and drew a line and then used the slope of that line. And then took another point closer and closer, and we said the actual slope is a limit of these numbers. Similarly, if you want to find the area, you will divide this interval into points and then say, okay, within this interval, I will take in the middle point, let's say, and approximate the area in this interval to be this rectangle. Same. So in each interval, I'm taking an approximation of the area of the curve. And say if I add all these areas of these rectangles, that is an approximation of the area under this curve from A to B. If I wanted a better approximation, I would divide it into more intervals and then come up with a better number. And then more intervals. So I can come up with a sequence of numbers that are better and better approximation of the area. And we would say, oh, if these better and better numbers, the sequence of numbers, if it has a limit, it's going towards a single number, that we define as the integral or the area under the curve. Integral of the function from A to B. That's integral calculus. So for example, estimate the area, okay, of the function x squared plus 1 in the interval 0, 3 using this, partition of the interval from 0 to 3. We just made this big partition of the interval. So we'll say, okay, we are taking the value of the function at this point, and this point, and making rectangles. And it's easy to find the area. It's 1 times 1. This is 1. This is 2. Height 2 times 1. And this is 1, 2, 3, 4, 5. 5 times 1. So 5 plus 2, 7 plus 1, 8 is the approximation of the area. In fact, under here, we're trying to find the area here. It's an approximation. We can also do a different approximation where in this interval, before we took the function at the beginning point, we can take the function at the end of the interval and use that to approximate the area. Here, take this value, approximate the area. Here, take this value. Okay. So, in fact, I said something wrong. We are actually trying to approximate the area from 0 to 3, not 0 to 2. So here. So this is an approximation of the area, which in fact, obviously we are missing this part, and this part. But it's an approximation. If we take more points in the partition, then we will approximate it better, try to fill up this. And as we keep breaking it further and further, we get better and better approximations. Okay, here if we approximate like this, so this is 2 plus 3, 4, 5 plus 6, 7, 8, 9, 10. 10. Okay, so 2 different approximations. Now, if you take multivariable calculus, so now here we're dealing with a function f, which is a function of x and y. And let's say if you want to find the volume under here, see in a function of one variable, we try to find the area. But if we take a function of 2 variables, we can try to find not the area now, but the volume. That would be the integral in multivariable calculus. And before, the differential calculus was if you're given a function, find the slope, how things are changing. How things are changing is about the future. Where is the function taking us? What is happening to the price of something? So what is the slope of it? What is the derivative? What is happening? So derivatives is about the future, and integral is about the past. We're taking the area of the function that is known to us. Slope is telling us where it is going next. So if you have a function of 2 variables and you are at a point x, y, x naught, y naught, here's the function. So we can say, okay, what is the slope in the y direction, slope in the x direction? If you move in the x direction, if you're walking on this hill, will you walk down or up? Will the slope be positive or negative? So we can talk about derivatives in different directions, not only in the direction x and y, in any arbitrary direction. If I want to move in this direction, what is happening to the height of the function? So those are the kinds of things you deal with in multivariable calculus. That's the third calculus class. So differential mostly is calculus 1, integral calculus 2, applications and techniques, and then multivariable calculus is calculus 3.